Now, students, I hope everybody is fine, and the intuition of giving giving a lecture on Aufbau principle and Pauli's exclusion principle is to have a deeper understanding of the energy, the distribution of electrons in an atom, and what's the role of energy levels in distributing these electrons in an atom. And if I start with the concept that in atoms what we have is electrons, and electrons can have only certain permissible energies that we have understood, and these permissible states of electron we call as energy levels. So we have an atom, and it has energy levels, and the relative energies of the various energy levels for hydrogen and 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 hydrogen-like atoms. We can have a graph of that where we can show the state of energies. Now, let me call this 1, and let me call this 2, let me call this 3, and let me call this 4. So this axis will give us energy, and 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 here in the first state what we have is 1s, and then we have 2s, and we have 2p, and this 2p has 3 states. And then we can talk about 3s, and in 3s we will have 3s, and we will have 3p, 1, 2, and 3. We'll have 3p, and we will have 3d, 1, 2, 3, 4, and 5. So this will refer to 3d. And then we will have 4s, and we will have 4p, 1, 2, and 3. And then we will have 4d, 1, 2, 3, 4, 5, and this will be 4d. And then we will have 4f, and that will go with 1, 2, 3, 4, 5, 6, and 7. So this is 4f. It's just a crude idea about the distribution of energy in hydrogen atom and hydrogen-like atoms. And what we see is that in hydrogen and hydrogen-like atoms, they are having the same principal quantum number. And the orbitals that we have in the same principal quantum number have the same energy. So what does this mean is that this 2s and 2p orbitals have equal energies because they have the same n. And if we talk about 3s and 3p and 3d orbitals, they have the same energies. And then talking about 4s, 4p, 4d, and 4f orbitals, they have the same energies. And what can we say? What an orbital is basically? We cannot have a direct way of describing an orbital, but we can say that this orbital is a representative of a region where the probability of finding a particle is maximum. The probability of finding an electron is maximum. So we can see that for same principal quantum numbers, all the orbitals that are falling for now, they have to have the same energies. Now the atoms containing 2 or more electrons. Now this is true for hydrogen or hydrogen-like atoms. We call those atoms as multi-electron atoms. Now, if we have atoms of whose atomic number goes on increasing, we call them as multi-electron atoms, and relative energies of various orbitals in those multi-electron atoms where we have we can look for a crude graphical representative of that, where we see that in multi-electron atoms, these orbitals differ. There is a difference. There is a difference in their energies, and to go with this is I will have energy axis, and I will have the relative energy of various orbitals. And orbital, I have tried to define. So orbital is a region where the probability of finding that electron is maximum. The point is probability. It's not anything like exact over here. Now, for this, what would I go with is 1, 2, then 3, 4, 5, 6, and 7, and then here I will have S, say for example, and for n equal to 2 I have S, and then I have P, and for n is equal to 3 I will have S, then I will have P, and then I will have D. So we can see that the energy, this is the energy axis over here. Now in multi-electron atoms, we have differences in the energy of these orbitals that we are trying to talk about here. So then, this I will take the case for 1, for 2, for 3. Okay, it should have been very close to this. Okay, so then 4, where I'll have S, then I'll have P, and I'll have D, and I will have F. And this is how it will go on as we move with the relative energy of various orbitals in these multi-electron. These are multi-electron atoms. The atoms, they are having electrons more than that of hydrogen atom. Now what we see is here that different orbitals having the same principal quantum number it may have different energies. Okay, and for a particular main energy level, what we have here is that the higher value of this orbital quantum number has higher energy. So P greater than S, P greater than S, P greater than S, D greater than P in the particular energy level. And we can have a crude way of writing down the energy in a particular energy level would be something like that. This F orbital has the greatest, then D is less than F, and it is greater than P, and it is greater than S. So if I reverse it's S is less than P is less than D is less than F. So this is how energy distribution is within an energy level with respect to S, P, D, and F. So now when we go for the states where n is greater or equal to 3, okay, some orbitals belonging to the lower main energy level may have energy. This P can be a little bit higher. They may have higher energy than some orbitals belonging to higher main energy level. So we can have those distinctions, differences, where the orbital belonging to this level of n can have energy greater than that of the same orbital belonging to the next energy level. So that is a very important point to be kept in mind. And for that, if I take a simple example to go with that, in case of multi-electron atoms, what we have is suppose we have 3D orbital, and its energy is higher than that of its energy is higher than that of 4s orbital. So even though 4s is in the energy it has a quantum number 4, principal quantum number 4. It's in the principal quantum number 3, but the 3D of this quantum number has more energy than that of the 4s orbital. And in multi-electron atoms, what we have is that the energy of any orbital is governed. It's governed by principal quantum number and azimuthal quantum number. So N and L, they are playing the very principal role in terms of energies of electrons in those orbitals. So, so to move on from here, what would I proceed with is now suppose I have the orbital having some lower energy. Suppose we have n plus L. If we take particular n and particular L, and this n plus L has the lower energy. For the orbitals having equal to this n plus L, the orbital having lower value of n has lower energy. Now, for example, let's take a case of 4s orbital. Okay. Now, for this 4s, what is the value of n is 4, and what is the value of L for this 4s? That is 0. So what we are getting here is 4. Now, if I take the 3D, orbital, now for this n is equal to 4, and for D, what's the orbital quantum number? That is 2. It's not 3, it's not 4, it's 3. And what's the orbital quantum number here? That is 2. So this is going to give me 5. So here, with simple illustration, we can understand that why the energy of an electron in the 3 orbital is greater than that of the electron in the 4s orbital. So what we see here is that the energy that the electron has in 3 orbital is more than that of energy in the 4s state. Now, to move on from here, if we talk about the ground state of an atom and an excited state of an atom, and we understand that we have a transition, and we have a transition from one energy level to another energy level. So if I have an electron here, so if this is in the ground state, so this is a ground state atom, and if by giving some external energy with some particular value, this electron can go into some other energy level. So now this is my excited state of the same atom. Excited state of the same atom. So the state of an atom when all the electrons in it occupy their lowest energy level, as is required by principal quantum number and N and L values, we call this thing as ground state. Okay, and or we can also call it as a normal state. People should most of the times be in the normal state. So the same is the case with the atom. Now what is the case for the how to go with this case? In this ground state, an atom has the lowest energy, right? It's in the lowest possible energy state. When electron in an atom occupies some sufficient energy, it will go to some higher energy level, which is permitted by the values of N and L. It's not that electron will go anywhere that it wants to. There's no freedom. The atom is now said to be in an excited state. So once it is gone to some permitted level, now we call that this atom is in excited state. All right. So to say, now if I take an example of the lowest energy level in hydrogen atom, what's that? That is 1s. Okay, so the ground state of hydrogen atom is 1s. So you will say that 1s is the ground state of hydrogen atom, and it has one electron. So this s will carry one electron. So when 1s1 will represent ground state, it will represent ground state of hydrogen atom. And so to say, now if this electron is prompted to go to 2s level, then we will say this atom is in excited state, and that state of the atom will be defined as 2s1. This hydrogen atom is in excited state for the hydrogen atom. Now the excited states are unstable. That's clear. When the atom is in its excited state, it's unstable. And even though we understand that electron can hardly stay in the excited state for about 10 to the power of minus 6 seconds on an average. So the atom is trying to come back to its because this is an unstable state. The atom is trying to be in the best possible condition, and therefore the excited states are not possible under ordinary conditions. You will not have excited states under ordinary conditions. And to proceed on from here, now we would like to I don't know. We would like to talk about the having this foundation, the basic foundation of the arrangement of electrons in an atom. Aufbau came up with a principle, and this Aufbau principle is also this Aufbau principle is also known as a building up principle. Now, according to this principle, what this principle states is that the electrons in an atom are so arranged that they occupy orbitals in the order of their increasing energy. So the point is that electrons are going to have the orbitals in accordance with the energies E1, E2, E3, and E4. If we have, say for the sake of argument, if we have, say, four electrons, the first one will prefer to go to the lowest. And then the next one will go to the next higher. So this process will go on where we have this, what we call as increasing energy of these orbitals. So what we have is to have a sequence of increasing order of the energy of these orbitals, and that will be the precise way for electrons to be in an atom, and to that atom to be in a very stable state. So what does it mean is that the orbitals with the lowest energy level will be filled first. So if we have, say for example, hydrogen atom, it has one electron, it's not going to go into the other energy states that are available in the hydrogen atom. It will go to a state which has the lowest possible energy. And since the energy of the orbital in the absence of any magnetic field, it depends upon the principal quantum number n alone, okay, and the orbital quantum number L. Hence, the order of filling the orbitals with electrons may be obtained from some basic generalizations. Now, what is that generalization? What we have is that this n plus L should be in the lowest. That means it should be in the lowest. It should be in the first state. And the next important point is that when two orbitals have the same value of n plus L, same value of n, the orbital having the lower value of n is filled first. So the orbital which has lower value of n, that will be filled first. And the order of filling of various orbitals is obtained by using these basic general rules. And I would like to go with that order. It's always good to have that order in mind. And what's that? This is my 1s, and then what I will have is 2s and 2p, and then what I have is 3s, 3p, and 3d. And what then I have is 4s, 4p, and 4t, and 4f. And then what I have is 5s, 5p, and 5t, and 5f. Then what I have is 6s, and 6p, and 6d. And then I have what is 7s, and 7p. Now, in order to have the idea in the mind, so that all these orbitals are arranged in increasing order of their energies, all we have to do is to start from here. Okay, so we'll start from here, and then we'll go back, and then we'll come back here. Okay, and then we'll go back, and then we'll come back to 2 2p, and 3s. Okay, so it's going like this, it's going like this, and then what we will have is from, okay, 3s is here. Now then we will have from 3p, and then it will go to 4s. Okay, and then we will have 3d, and 4p, and 5s. Then it will go like this. Okay, so this is all going in the increasing order of energies of these orbitals. So then 4d, then 5p, and 6s. And then we will have 4f, and 5t, then 6p, and then we will have 7s, and it will go like this. And then finally we will have 5f to 6t to 7p, and like this. And we can have those things where we get an idea where we have to come back. Okay, this is how we have to come back, and this is how we have to come back, and this is how we have to come back, and this is how we have to come back. So this is the simplest way to determine the relative energies of different orbitals. So if I have to write down this, I can write down this as, I'm starting from 1s. It is the lowest energy of the lowest orbital. Then I have 2s. Then I have 2p. Then I have 4s. Then I have 1s, 2s, 2p, and then 3s, then 2p, then 3s. Okay, then 3s, then 3p, 4s, and 3d. Then 3p, 4s, 3d. All right, 4p, 5s. Then we have 4p, 5s, 4d, 5p, 6s. Then we have 4d, 5p, 6s, and then we have 4f, 5d, 6p, 4f, 5d, 6p, and then we have 7s, and then we have 5p, and so on and so forth. So this is how the electrons can be distributed in multi-electron atoms in increasing order of their energies, and we call this principle as Aufbau principle, that gives us basically the arrangement of the electrons in multi-electron atoms, that how we can have arrangement of these electrons. If for the sake of argument, if I take sodium, which has atomic number 11, so what I will have is 1s2, 2s2, 2p6 and 3s1. This is how the electrons will be configured in sodium atom. This is how electrons will be in their respective orbitals in terms of their energies. And to have the final touch of this video is that three. Now, what is important here is that that what is it that all the electrons will go in some particular energy level? Can we have many electrons in the same orbital, and how these electrons can be distributed among these orbitals? And what was most important principle that was given by Wolfgang Pauli? It was Wolfgang Pauli. And he came up with the principle in 1925 known as Pauli's exclusion principle. Pauli exclusion, as we understand, exclusion, out. And this principle is very useful in constructing the electronic configuration of these multi-electron atoms. Now, what this principle states is that no two electrons in an atom, no two electrons in an atom can have same values for all four. How many quantum numbers we have? All four quantum numbers. And this can be put in place by virtue of an example. Suppose I have, for example, I will take a case where I have an electron. We have two electrons for some particular case. If I go with that, and I have electron 1 and I have electron 2. If I go in terms of its quantum numbers, okay, their n can be same. They can be in the same principal quantum number, 0 orbital quantum number, same magnetic quantum number, but they will have opposite spin. So this positive sign before 1/2, it basically refers to the orientation of the electron in terms of clockwise and anti-clockwise spin of the electron. Thus two electrons having the same value, they have same value of n, n. They have same value of l. They have same value of m, but they cannot have the same value of spin. So two electrons cannot have same set of quantum numbers in the given shell. So that's what we can say is that the two electrons that we have the same values, can have different. They can be different in their spins because their spins are in opposite direction. This leads to the very significant observation, and that is each orbital that we have, each orbital can accommodate at the maximum two electrons. And this limit is signifying that each orbital can accommodate at the maximum two electrons with opposite spin. So if you have an orbital and it has to carry the electrons, all it can do can take two electrons, but their spins should be opposite. And this can be another statement of Pauli's exclusion principle. And this principle leads to many important conclusions, like an orbital cannot have more than two electrons. So there is a restriction for electrons to be in the orbital, right? And these electrons are basically fermions. And in any main energy level, say n, the maximum number of electrons is twice the total number of orbitals, or it is simply equal to 2n squared. So if we have, say for example, if we have s orbital, it's a single orbital. All it can have, the maximum number it can have is double the number of its orbitals. So it can have two times it has one orbital, so it can accommodate two electrons. And in the same way, for p orbital, it has px, py, and pz, and it can accommodate 2 times 3, that means 6 electrons. And there will be each pot for these orbitals carrying two electrons each. And this is what we get as a general formula known as 2n squared, where n is referring to the principal quantum number. So what we understand here is that what is the practical way of allocating these electrons in multi-electron atoms, and we have seen two important rules. One is given by Aufbau, who basically gives out the way through which all the orbitals that are lying in a multi-electron atom in their increasing order of their energies. And then there is a restriction from Pauli exclusion principle, where it states that you cannot have two electrons in an atom who have the same set of 4 quantum numbers. So with this, I would like to stop.